Hello everyone, I am Admile N.S. So today in this video we are going to study the two important points regarding flip-flop. So the first point is conversion of flip-flop and the second point is race around condition. So for the conversion of flip-flop we have to study the two important conversions. So first one is a conversion of SR flip-flop into JK flip-flop and second is conversion of JK flip-flop into SR flip-flop. So in earlier video we can study the various conversion of flip-flops. So in order to convert the one type of flip-flop into the another type of flip-flop, we have to consider the excitation tables of the flip-flop. But in some cases, while consider the excitation table, some errors can be occurred. So how to minimize that kind of errors? So if we have to convert the SR flip-flop into JK flip-flop, so in this case the required flip-flop is JK flip-flop and the available flip-flop is SR flip-flop. So if we consider the excitation table of required flip-flop, that is a JK flip-flop, so in the excitation table of JK flip-flop it consists of don't care condition. So if we consider as it is required flip-flops excitation table, then our first and second column contains some don't care condition. So it is difficult to obtain the K-map equation while considering the don't care condition. So instead of the excitation table we can consider the truth table of required flip-flop. So in this case our required flip-flop is JK flip-flop, so we know the truth table of JK flip-flop. So here we can consider the total truth table of JK flip-flop, that is a JK, QN and QN plus 1. So we can consider the truth table of JK flip-flop, and after that we know the available flip-flop is SR flip-flop, hence we can consider the excitation table of SR flip-flop. But our excitation of SR flip-flop consists of 4 rows, but in this case we have a total 8 rows. So how to draw the excitation table for SR flip-flop? So in order to draw the excitation table of SR flip-flop, we have to consider the present state and next state. So while observing the excitation table of SR flip-flop, so as the present state Qn is 0 and Qn plus 1 is 0, so for 0 0 we have to observe our excitation table of SR flip-flop. So in our excitation table of SR flip-flop, for input 0 0 there is a output SR flip-flop consists of 0 cross. For 1 1 in excitation table of SR flip-flop there is a cross 0. Again for 0 0 our SR flip-flop consists of 0 cross. For 1 0 the SR flip-flop consists of 0 1. For 0 1 the SR flip-flop consists of 1 0. For 1 1 SR flip-flop consists of cross 0. Again for 0 1 the excitation table of SR flip-flop consists of 1 0, and for 1 0 again it is a 0 1. So depending on the present state and next state we have to consider the excitation table of SR flip-flop. So after considering the excitation table of SR flip-flop we have to draw the K-map. So how to draw the K-map? So in the JK flip-flop, the JK flip-flop consists of two inputs, that is a J, K. So one input is J, other input is K, and we have to consider the present state Qn. So in this case the total 3 inputs are present, so that's why we can consider the 3 variable K-map. So depending on the 3 variable K-map we have to consider the equation for S and R individually. So first we have to draw the K-map for Sn and then we have to draw the K-map for Rn. So while drawing the K-map we have to consider the cell numbers from 0 to 7 because there are 3 input variables are present, so we can consider the cell number from 0 to 7. So depending on the cell number we can draw the K-map for Sn and K-map for Rn. So after drawing the K-map for Sn and K-map for Rn, we get the equation as Sn equal to Jn into Qn bar. So if we consider the 3 variable K-map we can form a 1 pair. So depending on a 1 pair we can form the equation Sn equal to Jn into Qn bar. So similarly for Rn there is a 1 possible pair, so depending on this pair we can write the equation as Rn equal to Kn into Qn. So how to draw the flip-flops? So to draw the flip-flop, we have to always consider the starting flip-flop. So the starting flip-flop is SR flip-flop. So we can draw the diagram of SR flip-flop. So it consists of input S, R, output as a QN bar. So our first equation is Sn equal to Tn into QN bar. So for multiplication we can use a AND gate. So for Sn, the Tn will become from this side and the QN bar, that is, come from the right side. For Rn, Kn into Qn. So for Rn, the input Kn from will take from left side and the output Qn. So here we have to take from the Qn. So we have to draw the right side of Qn, and that right side of Qn is connected to the input of second AND gate. So in this way we can convert SR flip-flop into the JK flip-flop. So the another conversion is the conversion of JK flip-flop into the SR flip-flop. So similarly we have to consider our required flip-flop. So here the required flip-flop is SR flip-flop. So if we observe the excitation table of required flip-flop, it consists of don't care condition. So if the don't care condition is present in required flip-flop, so instead of excitation table we can consider the truth table of required flip-flop. So here we can consider the truth table of required flip-flop, and whatever the available flip-flop, we have to consider the excitation table of available flip-flop. So that excitation table we can calculate it from the present state and next state, that is a Qn and Qn plus 1. So for 0 0, if we observe our excitation table of JK flip-flop, so for 0 0, 0 cross condition is present. For 1 1, cross 0 is present. Again for 0 0, 0 cross is present. So like this we can consider the excitation table of JK flip-flop. So after considering the excitation table, again we have to draw the K-map equations. So here again SR flip-flop consists of two inputs, that is a S, R and present state Qn. So we have to draw the 3 variable K-map. So here we can find out the equation for Jn and Kn. So after forming the equation for Jn, so Jn will get Jn is equal to Sn and Kn will get Rn. So how to draw the flip-flop conversion? So our example consists of first flip-flop as a JK flip-flop. So we can draw first flip-flop as a JK flip-flop. So the input as J, K and output as Qn and Qn bar. So from the equation Jn is equal to Sn and Kn is equal to Rn. So in this way we can convert one type of flip-flop into the another type of flip-flop. So the next important point is a race around condition. So basically we need to understand what is the race around condition and in which flip-flop the race around condition can occur. So always keep in mind the race around condition always occurs in JK flip-flop. So how to identify the race around condition? So for race around condition, there is a for JK flip-flop, if the J input and K input is equal to 1, and we know we can consider the clock pulse also as a 1. So for JK flip-flop, if the value of J input and K input is 1, then the flip-flop goes into the toggle state. So it is meant by a toggle state. So for toggle state we can get the invert output. So if we have a 0 input, then we'll get a output as a 1, and if we have a input as a 1, then we'll get output as a 0. So in this case we have a multiple toggling input. So how to consider the multiple toggling input? So if we consider a clock pulse as a input, so the clock pulse can be continuously changes from 1 to 0 and 0 to 1. So if our input J as a 1, so here we can consider input as a 1, so our clock pulse is too long. Similarly, the value of K is also 1, then also our clock pulse is too high. So in this case we also we also expect the whatever the output of JK flip-flop, that output of JK flip-flop will also the continuous clock pulse. But as the clock pulse is too long, then the next state of JK flip-flop can be continuously changing. So here we can consider the continuously changing clock pulse. So whatever the long clock pulse, that long clock pulse can be continuously changing with respect to present state. So here we can observe the clock pulse can be continuously changing as the J and K is equal to 1. So here we can observe the multiple toggling effect. So that multiple toggling effect is called as a race around condition. So in order to remove the race around condition, we can use a master slave JK flip-flop. So the master slave JK flip-flop nothing but the combination of two SR flip-flops. So here we can draw the state diagram of master slave JK flip-flop. So in this case we can consider one SR flip-flop as a master flip-flop and another SR flip-flop as a slave flip-flop. So in this case we can provide the clock pulse is, we can consider the one clock pulse to the master flip-flop and inverted clock pulse to the slave flip-flop. So why we consider the inverted clock pulse to the second flip-flop? So if we provide the clock pulse 1, the master flip-flop will be unable, and as we know we can provide the inverted clock pulse to the slave flip-flop, so the slave flip-flop can be disabled. So in first case, if clock pulse is 1, the master flip-flop will be unable and the slave flip-flop will be disabled. So whatever the input we can provide to the master flip-flop, so same output we can get at the output of master flip-flop. So as the second slave flip-flop is disabled, so the same output will get at the end of flip-flop. Means here the toggling effect can be removed. So whatever the same input provided by master flip-flop, that same output we can achieve at the end of output flip-flop. So in another condition, if we provide clock pulse as a 0, so in our master flip-flop will be disabled and the slave flip-flop will be enabled. So whatever the output of master flip-flop, that will remain same at the output of slave flip-flop. So in this case we can avoid the multiple toggling effect. So in order to remove the race around condition, we can use a master slave JK flip-flop. So the master slave JK flip-flop can simply use the two combination of SR flip-flops. So the whatever the second slave flip-flop, that can follows the output of master flip-flop. So in this way we can avoid the race around condition by using the master slave JK flip-flop. So thank you.